This is the neuron story. An event happens in cell A such that a neurotransmitter travels across the synapse of cell A and cell B. There are several possible outcomes as the neurotransmitter crosses this space. The neurotransmitter molecule can be taken up into the presynaptic membrane through a process called reuptake. Another option is the neurotransmitter molecule can dissipate in an interstitial fluid or float away, or the neurotransmitter can be metabolized through enzymatic degradation, or the neurotransmitter can bind to the postsynaptic membrane. Okay, let's go back and explain that. Well, starting with what an event actually is, an event could be anything in the world that requires your brain to decide that you need to make some sort of action. It is as simple as breathing, it is as complicated as ballet, but whenever an event happens, it causes the neuron story. It starts with a neurotransmitter traveling across the synapse of cell A and cell B. Let's say the synapse is more of a parking lot between two buildings. Before any kind of motion or action can be produced, you have to make it from one side of the parking lot to the other. Now, as I said before, the molecule can be taken back up into the presynaptic membrane through reuptake. Reuptake is basically the cell A building decided that it needs its neurotransmitter back. A really windy day outside, and so that neurotransmitter never makes it across the parking lot from cell A building to cell B building. However, in the best case scenario, the neurotransmitter makes it to the cell B building, to the binding site of the receptor, which is located on the dendrite of cell B. The neurotransmitter then causes the ionic receptor to open that is permeable to the ion pore. The ion will move across the opening because of two forces acting upon it. These forces are osmosis and electrostatic pressure. The binding of the neurotransmitter molecule thus allows the ion to move into cell B. The movement of charged ions appears on the oscilloscope initially as a short burst of depolarization and is called an EPSP, which stands for excitatory postsynaptic potential. The accumulated charge moves along the surface of the cell body, also known as the soma, and sums together at the axon hillock. The accumulation of charge is due to the process of temporal or spatial summation and reaches a reading of negative 75 MV, which is called the threshold of excitation and is necessary to open the voltage-gated channels. Once the action potential is initiated, it continues through several phases. The rising phase is the rapid hyperpolarization and is associated with the movement of ion sodium into cell B. The falling phase is the rapid depolarization and is associated with the movement of the ion potassium out of the cell. The action potential appears to travel the length of the axon by a process called saltatory conduction. This means that the charge appears to jump to and from the node of Ranvier, which are spaces of exposed axon. These spaces occur between a fatting covering called the myelin sheath and the central nervous system. The covering is made from glial cells called Schwann cells, and in the peripheral nervous system it is made from glial cells called oligodendrocytes. When action potential reaches the end of the axon terminal, sodium ions enter the cell and serve as a signal of movement for the neurotransmitter, which contains the vesicle molecules. These small containers move to the end of the postsynaptic membrane and merge with empty the contents in the synapse between cell D and cell C. That is the end of the neuron story.